We'll move into our agenda with a general overview that I'll provide, give you some feedback or input on an overview of details about MOSAiC, what happened in the field, etc. We'll hear from Scott Giangrande about ARM data products and an overview of some of the activities there. We'll hear from Mike Gallagher about a merged data set that he's putting together for the MOSAiC data. And then we'll get into a bunch of science bites. So these will be very short presentations from many of you all about different science activities that are ongoing or things that you have planned, etc. So you can see the list of people there. These are, the suggestion was 1 to 3 slides and 4 minutes max. Many of you all interpreted 1 to 3 slides as maybe 13 slides. Maybe I got that wrong. So anyhow, I hope you all can stick to the 4 minutes so that we can then have some time at the end for questions and discussion, which I think is really important going forward with this great new data set. So without further ado, we will go right into the presentations, and I'll start with an overview presentation. So let's try to make that happen here. Okay, you should now see a slide here. Can somebody confirm that you can see that?
Yeah.
Good.
Great, thank you. All right, MOSAiC. So the title here, Challenges and Opportunities of a Year in the Arctic Sea Ice. I think you'll see in a lot of pictures coming up that there were a number of challenges, but I think that this also provides us with this fantastic opportunity to study the Arctic system, and hopefully you'll see why. This presentation is a modification of one that I've given a number of times, and so I've kept a couple slides in here on things like motivation, Arctic change, and so on. I'm not even going to talk to those slides or the kind of basic initial plans for the expedition. I'm leaving them in here for kind of the record, so people can go back and look at those if they are interested. But really what I would like to do is get on to what happened. How did things go? And this is a picture of the polar stern icebreaker as it's sitting in the Arctic sea ice. At the bottom of the page, you can see the overarching question that was motivating MOSAiC. What are the causes and consequences of an evolving and diminished Arctic sea ice cover? So that question really, the causes side of it really speaks to the processes, and the consequences are, the implications of Arctic change on a coupled system, on a global system. And so let's take the voyage of this icebreaker as it goes across the Arctic, and we'll take a look into some of the science and some of the activities that happened along the MOSAiC path. And I will use this map as a vehicle for taking us on that journey. We're looking down at the North Pole. There'll be different colors for different legs of the mission. There were 5 legs of this mission where we rotated crew and personnel and supplies and fuel. So this is the first leg in red there. We started in early October. We actually left in late September from northern Norway and went out and plugged in the ice and then passively drifted with that ice over the course of the year. And so this is the first leg where we installed things. We started some of the sampling programs and we found some really interesting ice conditions. And so I'll take you on a bit of a photo journey, and the photo journey starts here. This is actually in Norway before leaving, and look at this team. This is the team of all the ARM ASR type folks that were there at the start. Pretty impressive, actually, to see such a commitment to this project and so many great people there to set things up, a lot of managers there and others. So it was really nice to see DOE's major commitment to MOSAiC from the very beginning. We loaded all kinds of equipment on board the ship. Here's a scanning radar going up to the top of the ship's decks. Here's a bunch of containers going on to the bow of the ship. And then once we were all loaded, we started to venture out into the sea ice. And here initially towards the edge, you see small ice flows, but eventually we found some bigger ice flows. We explored those and found one that we were going to call home for the rest of the year. And then we started setting up all kinds of equipment. So here's a picture of one of ARM's radiation stations out on the ice near the ship. So a lot of the equipment was on the ship, but some of it was out on the ice away from the ship, so that we could really get this nice perspective undisturbed by the ship itself. We set up all kinds of things out there. This is a view from what's called Met City, looking back towards the ship. And one thing you can notice right away here is it's pretty dark. We right away descended into the darks of polar winter that lasted for about 4 months. So that was a big challenge, of course, but really a cool opportunity for us. We set up all kinds of equipment. You know, ARM was a major player, but there were so many people and nations and institutions involved. I'll get to that a little bit later. We set up buoys all over the place, different stations, all kinds of devices out on the ice for looking at the Arctic system. And then we started a very comprehensive program of physical measurements and samples. So here's a guy measuring some snow properties. We're looking at the snow, the sea ice, the ocean, the ecosystem, biogeochemistry, and of course the atmosphere. And that's a big part of what ARM was there for. And right away, things were interesting. The ice was dynamic. Here's a picture from the side of the ship with a crack that went right through our camp. This is in the early days, and we got a quick taste of what things were going to be like. You can see some other leads forming out by some of our installations out on the ice. In the foreground, you see some skidoos, some power lines, some tents in the background. So this actually made it very complicated. Scientifically, right away, here's some measurements of aerosol total number particle number concentrations from a CPC. This is a nice ARM measurement from the bow of the ship. This is unfiltered data. These are just raw quick looks that we were looking at in the field. And we saw some really interesting things right away. First off, in this diagram, this is about a month's worth of data from middle of October to middle of November. And what you can see is a wide range of particle number concentrations and some values that are extremely high. And this is ship pollution. Well, we couldn't avoid it. We sampled the ship's pollution at times, and there's a lot of effort underway to try to filter that out and identify those periods. But something that's actually really interesting in the data is all these time periods, I've circled a couple of them in green, where the total particle number concentration is less than 10. Sometimes it's down to single digits. And this is actually pretty remarkable. There are basically no particles in the Arctic atmosphere at this time. And the suggestion then is that, hey, with no particles, you can't have clouds form. So it'll be interesting to look at this, but one initial insight into some of the variability of aerosols in the Arctic. Some of the early observations of clouds and cloud phase. So here again is a 25-day time period from the fall of 2019, where we're looking at time series and time height cross sections from the radar and LiDAR in the top two panels. So you see clouds at a variety of levels, some deeper, some shallower. The LiDAR with the red areas kind of shows strong backscatter that suggests liquid water. And indeed, the liquid water path derived from microwave radiometer shows there was liquid water at this time when temperatures are cold. So these are temperatures at minus 10 to minus 20 degrees Celsius. And then the bottom panel is the radiation. And you see upwelling and downwelling long-wave radiation. And when you see a big difference between those, that's a deficit at the surface. That's the surface cooling, and that happens when there's no liquid water clouds. Versus when there are liquid water clouds, you see those two curves are very close to each other, that near radiative equilibrium at the surface. This is a typical view that we kind of understood about the Arctic, but indeed MOSAiC was very similar. And then in this next panel, I take that same radiation at the top and then plot a couple of other things. So some of the other heat transfer terms at the surface: conductive, sensible, latent heat fluxes, the total surface energy flux, and the surface temperature. And I'm not going to go into the details here, but you see a lot of variability in these different energy transfer terms that are driven largely by the radiation and the cloud-driven radiation. And importantly, if you look at panel D, the surface temperature is meandering all over the place, and it's generally warmer when there's liquid clouds and colder when there's no liquid clouds. And this signature actually penetrates down into the sea ice, and that's the bottom panel on the right. These are temperature profiles in centimeters through the atmosphere, through the ice, and down into the ocean. The ice boundaries are approximately those white lines there. And so what you see is when there's these periodic warm periods driven by cloud radiation, you see the warmth actually effectively penetrate down through the sea ice at times. So this can have an effect on the ice as it's growing during its growing season. You can see the bottom line is actually getting deeper as the ice is growing thicker. So just a quick snapshot into some of the cool kinds of processes that we can look at, these interactions between the atmosphere, energy transfer, and the sea ice itself. Let's jump into leg 2. Leg 2 was the middle of winter, and you can see the yellow there is the leg 2 drifting time period. No sunlight during this time period. The ice dynamics chilled out a little bit for us, fortunately, and the temperatures also chilled out. We got to minus 43. Here's just a great picture taken by Michael Gallagher, who's should be on this call here, of one of the flux stations that came from our group, actually out at a remote site away from the ship. But you can just see the fantastic kinds of views and scenes that we had out there in the sea ice. And one of the great questions about the wintertime is what happens to biology in the Arctic winter? We have all kinds of great samples of the biology, and we had a great ecosystem team out there. And now biology, I know, it's a bit of a stretch for ARM, right? It's kind of out there a bit, but interestingly, there's actually a joint Genome Institute project to look at some of the microbial communities and their metagenomes and transcriptomes out there at MOSAiC. And JGI is another DOE user facility. So this is a tremendous opportunity to link some of the types of observations from the ARM user facility with another DOE user facility out there during the winter time at MOSAiC. Moving on to leg 3, this was a long leg. You can see the green line there is longer than some of the others, and that's in part due to COVID. COVID complicated our ability to rotate people, and so some of the folks out there were trapped out on the ship for a couple months longer than they had planned. So a complicated time, but also the circulation pattern set up in a way that really pushed us across the Arctic faster than anticipated. And there were some nice events along the way. I'll illustrate that a little bit here. This is a time series of the monthly values of the Arctic Oscillation Index. The Arctic Oscillation Index is an index that tells us about the large-scale circulation of the Arctic system. And it turns out that in the first 3 months of 2020, as we're out there near the North Pole, the Arctic Oscillation Index was at record high positive values. And well, what that means is that there actually was a very strong polar vortex at the time, which contributed to the biggest ozone hole ever observed there. But it also meant high and anomalous winds at our site. And so this diagram is a composite analysis of the 1,000 millibar winds for the months of January, February, March 2020. And what you see is, here's the North Pole, and the ship was pretty close to the North Pole, heading towards Fram Strait, so kind of up in this diagram towards Fram Strait. And you see this green bullseye there, which is anomalous winds of 3 to 4 meters per second. And you can see the wind vectors there. So kind of blowing us along this trajectory faster than anticipated. This is, of course, anomalies relative to the long-term climatology. So we were on a pretty rapid ride across what's called the transpolar drift. Another interesting diagram from the time is, again, a cross-section of temperature through the sea ice. So at the very top is the atmosphere. You see the sea ice in the middle, and then there's kind of a bottom of the sea ice that separates down to the ocean. And of course, the ocean is all at about its freezing point, which is about -2 for salty ocean water. Over time here, you see a year day, and 0 is the new year for going into 2020. You see the growth of the ice happening, and you see these events, these pulses of warmth coming from the atmosphere, driven by storms, driven by advection in the atmosphere. And these things are affecting the thermal structure of the sea ice over the course of the year. But I want to draw your attention to about day 120, where we started to see this important transition. This was mid-April. There was a warm air advection event, a warm air intrusion that brought lots of warm air into the Arctic. It was kind of a shift in the large-scale circulation. And you can see that the ice really warmed up during this event, and it never really cooled down after that. It continued its march towards warming, and towards the far right side of this diagram is when it finally reached the melt onset, wherein the sea ice was all at its melting point. So pretty interesting progression. A lot of this driven, of course, by atmospheric variability. So it's important for us to characterize that. Of course, at the time, we're cruising across the Arctic very fast, being blown by the large-scale circulation pattern. So there were lots of dynamics, and you can see some very nice features here, leads and ridges. Here's a view from the ship looking out towards what's called Met City and a bunch of the ARM equipment out there. And you can imagine that the commute out to work today was a little harder. And so some of the folks that were out there this time struggled to keep things operational. Okay, let's get into leg 4. The transition between leg 3 and 4 required actually the ship to come out of the sea ice. And this was in large part due to COVID and the complications there. We lost access to a couple of the vessels that we were going to use. So there was a bit of an interruption out at the ice floe. We did leave some equipment behind, fortunately, to bridge that gap, but then got out to the ice again, the same ice floe, although that the MOSAiC ice floe had broken up a bunch, as you'd seen in the previous pictures. Here's a nice picture from the time. It shows kind of the installation of all the equipment that we had here, relevant for the ARM AMF2. You can see on the bow of the ship a number of containers, the kind of familiar sites that we're all used to from ARM equipment. Also lots of equipment installed up on top of the ship along the railings. So that's kind of the onboard stuff. And then you can start to see some of the things out on the ice. Way off in the distance there, ARM had some installations out at Met City. This is a slightly different version of Met City than the previous one with all the cracks, because we had to move some things, of course, and reinstall some things. And there's a number of other installations on the ice. You can see the whole ice floe right now from this helicopter picture, a nice big circle about 1 kilometer across at this time in the middle of summer. Of course, the sunlight is very strong now. It's 24 hours of sunlight for quite a number of months. And you can start to see melt ponds forming on top of the sea ice as we move into this summer melt season. Just to show you some of the complexity, this is a map looking down vertically, laser scans from helicopter to look at the terrain. And I've kind of provided a gray outline of the MOSAiC flow. And in the lower right-hand corner, you can see the ship there. So this is all the stuff we had out there. There's green lines that are our pathways, all kinds of little shapes that are colored, that are different installations, equipment out there, people looking at melt ponds, measuring the ice, looking at albedo, sending underwater vehicles under the ice, flying drones above the ice. Tons of activity here on this ice floe to really monitor all aspects of the evolution of the ice. A couple nice pictures from the time. You can see melt ponds. Of course, those complicate our ability to move around the ice. We had to get a little creative at times. People making ice cores to look at what's happening in the ice, how it's changing, what kind of biology is in there, what's the physics involved. People looking at snow depth, melt pond depth, ice thickness, measuring surface albedo over a variety of surfaces. Here are some people that are sending devices down into the ocean to measure the ocean structure in the foreground. In the background, this is part of Heist de Boer's team flying unmanned aircraft to look at the atmospheric structure. Here's a nice view down into the ocean at the time. You know, in summertime, you get all this melt and that's pouring all this fresh water into the ocean that of course is salty below. So you get this really interesting stratification right near the surface that can affect things like gas transfer and energy transfer. Really fascinating time of year. So leg 4 ended in a spectacular disintegration of the ice floe at the ice edge. So this is really, we followed this ice floe until its very end of its life cycle. But we weren't through the end of the year yet, and we wanted to capture all seasons of the year. And so we took the ship then back north into the ice again to finish out the year and to get that transition from the summer into the freeze-up time period. This required a reinstallation again. You can see, helicopters used. There's some ARM equipment on the ground in the background as things are being reestablished out there on a new chunk of ice near the North Pole. A nice picture here, setting up a station to look at the freezing process as things like melt ponds and leads started to freeze over. This is a really important transition for the Arctic system to get us back to where we began our measurements over the course of the year. So how did that year look? This is the sea ice extent from the National Snow and Ice Data Center, and the gray shading in there is kind of the climatology, what we'd expect from long terms. And the blue line, the end of that blue line is the end of MOSAiC, and you can see that the summer sea ice extent was very low. It was not a record, did not beat 2012, but it was the second lowest on record. So a pretty important year as far as the sea ice, and we were out there in the middle of it as it was declining very rapidly. Modeling activities, a few statements here. There are a number of modeling activities associated with MOSAiC. Some near real-time verification of forecasts. We'll hear a little bit from Amy Solomon about that. Some development of merged observatory data files. So data files that are specifically designed for model evaluation. We'll hear a little bit from Michael Gallagher about that. Both of those activities are in partnership with the World Meteorological Organization's Polar Prediction Project and their Year of Polar Prediction, YOP. So a lot of those were specifically designed to help support model evaluation and development. But there's LES, regional, large-scale modeling, all kinds of modeling to examine many different processes. Some 70 discrete modeling activities are ongoing and or planned for the MOSAiC timeframe. So a large user community of modelers ready to take this kind of great information from MOSAiC. A little by the numbers, we had 20 nations involved in the funding of this and 37 nations involved in terms of participants on board. So really an extraordinary scope. 7 icebreakers or ships involved, more than 80 institutions, more than 400 people went to the field. And of course, a lot of money was spent and is still being spent. So to start to summarize a bit, well, we had some challenges, of course, sea ice dynamics, COVID, many other things, but really a lot of these challenges brought opportunities to engage the emerging Arctic. We were there in the middle of a thin and dynamic ice pack, and this is exactly the kind of conditions that we need to study and understand. We did tons of science, so we know a lot about the atmosphere here at DOE, but there's also ice research, ocean, ecosystem, biogeochemistry. We had a whole remote sensing team, we had an aircraft, we had modeling teams. So a very cross-cutting kind of scientific scope here for this project. ARM, of course, played a major role on the atmosphere team. But I do want to emphasize that as big as ARM's contribution was, MOSAiC was huge. We had so many different participants. Broad participation internationally, interagency, interdisciplinary. And we built a lot of capacity, a whole new generation of trained field scientists and new concepts for research on thin ice. I've included in the presentation here a couple summaries of data as I see them. I'm not going to go into these in detail. I wanted to leave them in this presentation just for people's information. It lists all the instruments and some of the basic measurements those are made for different realms, different types of observations. And I've color-coded those based on kind of a quick and broad judgment of the quality of data. Green means everything was pretty much behaving as it should. There might be periods of a little interruption here or there, but generally the instruments were doing what they should. Yellow means you should use some caution in interpreting the data and or there were some complications. Red means, yeah, things didn't go as well as we had hoped. I'm not going to go through all these, but you can see there's atmospheric state and radiation, lots of measurements there. Cloud, precipitation, things went pretty well in general, other than the scanning X-band radar that failed before we even started. Aerosols and gases, you see a lot of yellow here, and that's not because this is bad data. This is because pollution. We had ship pollution that could affect all these kinds of air samples and air measurements in various ways. And so this is an area where you definitely need to use some caution when interpreting any of the aerosol and gas kind of measurements. But fantastic observations in general. And just briefly, scientific pathways forward. We'll hear from a number of different people that are doing some work here, but I'm just listing some of the various topics where I think we have a great data set to dive in. Of course, ice thermodynamics and the cloud impacts on that. Winds, momentum, ice dynamics, the balance of dynamics and thermodynamics for understanding things like sea ice forecasts, aerosols. There's so much to do with aerosols. So many firsts here, looking at sources, processes, cloud activity, and more. Precipitation and snow on sea ice. That's an evolving and important topic, and I think we can do a lot there. Cloud microphysical and radiator properties. I mentioned the JGI microbial analysis that's ongoing. There are a lot of opportunities for coupled system science here. Development of data products, high resolution modeling, looking at clouds, looking at boundary layer structure and other processes, and of course, all kinds of model assessment and development. So we're really just getting started here, but you can see that there's such a broad scope of things that can be done with these great data. And I couldn't give a presentation here without some polar bears, so there we go. And I'll just summarize by saying DOE rocked MOSAiC. DOE did an awesome job out there and continues to do that through investments in science. And so that's my summary of the MOSAiC field ops. And I think overall it went very well, and we have a great data set to really feed science going forward. So with that, I guess I'll open it for any quick questions that you might have, but otherwise I want to transition on towards hearing from Scott Giangrande in the ARM data product side. Are there any quick questions at the moment?
Matt, I don't know if you can see the hand.
Yeah, cool.
Yeah, I've been curious about that. You showed the how the ice temperature really warmed up very suddenly with that mid-April, late April time period with warm air advection from the south. Has anyone really looked at the ocean temperature below that cross section? Because I'm wondering if the MOSAiC site was actually starting to get into a little bit warmer water at that time. So there was actually heating from below as well. Do you know of anyone who's looked at that?
I don't yet, but that's a great topic to look at. I mean, clearly we know that there was a major shift in the atmosphere, right? We know that part, and we know that it was a warm air intrusion. So, you know, that side of the thermodynamics, we do understand, at least conceptually. As far as the ocean, yeah, that's a good open story that I think people should definitely pursue.
Because I mean, the point was that, as you showed, MOSAiC was drifting very rapidly to the south, and you know, the summer month, Lake 4 that you showed, that was really in Fram Strait and east of Greenland, between Greenland and Svalbard. And so it really wasn't the central Arctic. And we're sampling, we're over different waters at that time as well. So I'm wondering if that contributed to the rapid warm up that happened in the ice. Because that's a little different than what happened at Sheba.
Yep, I definitely agree with that. Different part of the Arctic. Any other quick questions? We can get into some science discussion later on, but just any other kind of programmatic questions that people have, or we can also take those later after we see the update from the kind of programmatic data side.
Do you mind if I make another comment?
Is it focused on programmatics or is it focused on science?
Kind of programmatics, what you were talking about, and was that you know, we did capture both the melt onset there in very end of May and the end of melt in early September. So we were able to get the two really crucial time periods that we wanted in the original planning.
Yes, definitely. I'm just looking at the chat here. Maybe we'll get into some of those towards the end a little bit. I'd like to transition to hear about MOSAiC data sets and products. So Scott, if you could go for it, I'm going to serve this presentation up for you.
All right, thank you. Can you hear me?
Yes.
All right, good. Well, this is all very exciting, and thank you for the opportunity to get a chance to speak to this group. And I'm already getting new ideas based on your presentation. But my name is Scott Giangrande. I'm one of the ARM translators. I'm going to be giving an update, hopefully brief enough so we can get to science and discussion on MOSAiC and data sets and products. Next slide, please. So MOSAiC was an extremely extensive and successful campaign. And I think Matt has said in other slides that I've seen that the majority of the MOSAiC data sets are available. And I think that that's something that's really unique, and we would like people to start downloading and using that data. One thing I will point out from the outset is that the mentors, this is a fluid and ongoing process. The mentors work very hard, and they will continue to update and improve the data sets. You know, I've done my best, specifically with help from Adam Tyson, Karen Johnson, and others, to come up with a couple of Gantt charts or displays for data and availability. And it's trying to simplify something that can't often be simplified. So I just want to point out that, you know, if you have any questions or if you have any concerns, certainly you can always feel free to reach out to myself, Damao Zhang, who's the translator, point of contact for MOSAiC, Adam Dyson, or most specifically the instrument mentors, if you really think that there's something that I'm missing or you have specific questions. But next slide, please. So kind of in that Gantt chart sort of style of looking at the overview of the campaign, you know, I'm not focused so much specifically on individual instruments here. I'd just like you to focus on the vast majority of green on the plot, that there's a lot of data available and it covers the vast majority of the campaign, and specifically many of the areas for which you see that that may not be data available. It's not that the data isn't there, it's just currently in process. And a lot of the data that isn't there is just gaps temporarily for the transit times. I do try to make special notes, and these slides can be available or other information later, of specific instruments and specific nuances. I think Matt had talked about the MWR3 channel, and there are some instances like that, or the TSI, where some extensive processing or other efforts will have to take place, but that doesn't necessarily always mean that that data is not useful. But on the whole, a lot of green, a lot of data is already there, and a lot of the gaps that you see on this chart will be filled in the future. Thanks. Next slide. Sort of a second, it mentioned that MET-SADI or co-located instruments on the ice as well. You know, we have similar displays. I actually don't mind showing you a plot with a little bit of red and DQRs on there to kind of make a point that just because the data has a DQR and ARM doesn't always mean that it's bad or it's affected or that it's not useful. I will give some specific examples of, in this case, the GND RAD from a slide later on. But the thing to kind of stress here is that certainly if you have any questions or specifics to individual instruments, always feel free to reach out to the mentors as a first point of contact. But oftentimes the point to stress here is that there's a lot of data available. And again, most of the gaps that we have are sort of around those transit times where it's not that the data isn't available, it's just not currently available in the archive and it's being processed. Next slide. Very much same story with the AOS system. I think overall there was a lot of good data available, as Matt has alluded to. It's sort of in the same token. Just because the data is green doesn't mean there aren't other nuances that you may also want to speak with individual mentors about. But a lot of the data is there and it's available. Most of the gaps currently are instances where the data is being processed. I give a specific point of contact to the Brookhaven AOS team, Yannick Ewan specifically, but certainly for instrument mentors, that's a good point of contact if you have questions. One particular instrument of note was the ACSM, which is currently under data review for quality. And again, I would point you to both that team and the individual mentors if you have specific questions about specific instruments. Next slide. There were a lot of unique instrumentation or deployments for this campaign, and some of the mentors did provide some slides. This is one provided by Rob Newsom, who's in another session at the moment. The Doppler LiDAR was a really unique instrument. It was the first time deployment for this new particular Doppler LiDAR system, and it's the first time ARM has deployed a Doppler LiDAR on a ship-based platform. Because of some of the ship correction nuances that needed to happen and some concerns about pointing it vertically, they did operate it exclusively as a wind profiler. Rob and his team are currently working with the ADC to implement a correction procedure for that. I think the methodology is done. It's just in process right now. But certainly you can reach out to Rob for more information with the contact up there. Rob is also provided, but I can type in the chat later, a link for quick look images as well. So you can also get a sense of some of that data and his process as he's going along. But I think this was one of those unique data sets that exist for this campaign. And it's a nice addition to have some of these ship corrected data like this as well. So it's the first time for a lot of this. Next slide, please. As I had mentioned on that DQR report type of slide, sometimes those types of Gantt charts don't really give you all the details that you need. And this is one of those examples with the GND RAD system and the ICE RAD system. And Laura Rimanaki, one of the co-chairs of this session, has provided me this slide and is certainly the point of contact to speak to on many of these details with regard to potential QC RAD-like products. But again, sometimes simple plots don't really give you all the details. And this is kind of going a little bit more into depth into the availability of the ICE RAD systems. And I would once again point out that, yeah, we will try to simplify things for you, but I think it's oftentimes much better suited to go directly to some of the points of contact. And they're currently working on some, as I said, some of those QC RAD type products right now, and those should be available moving forward for this campaign. Thanks. Next slide. Another one of the key instruments or pieces of equipment that were available for this, and somewhat of I think probably everything is a unique deployment for MOSAiC, but in this case, this was also a unique radar type deployment. We had 3 operating radar systems during that campaign, 2 vertically pointing systems, a vertically pointing K-band and a vertically pointing W-band, as well as a scanning K-band cloud radar system. I'm highlighting some material that will also be featured on the radars on a poster by Karen Johnson on Thursday. So feel free to check that out and discuss radar activities with her as well, one of the radar data mentors. The key thing about MOSAiC that was really exciting was that there was fairly reliable uptime. This is a challenging deployment, and all of the radars, for the most part, were working for all of the times that they were supposed to be working, and that's really impressive. It's also one of the few campaigns that ARM has ever had where, and I know this will sound weird to some people, there's not that many examples of simultaneously having both vertically pointing K-band and W-band. So there are potential dual frequency type activities that can be done too. It just isn't that common, and that's probably surprising to some radar folks. But on the next slide, just as a continuation, if you are interested in using that data, we're currently in the process of going through what's sometimes called the B1 calibration step, which is trying to make sure that we can align those data sets properly. There are some known issues with the radar data sets. The Kaiser MD mode has a pulse compression filter. It's the mode that's most sensitive to higher clouds. Some of these are issues that cannot be corrected for. They'll provide additional artifacts and an additional offset, but you just have to work around them. But they're still workable data. So again, there may be a DQR on it, but it doesn't necessarily mean that you can't deal with that. Similarly, absolute calibration for a deployment like this was very challenging, but from initial discussions with partners, it does seem like the Kaiser general mode was fairly reliable and consistent with some of the natural scattering or types of intrinsic properties that you would expect for those environments. And that's what you would hope. The Kaiser in its general mode will usually be the calibrated gold standard. So you expect that to be the best reference. And so if you base everything off of that, there are some offsets that are a little bit problematic for some of the radars, but the one positive again is that the radars were running the whole time and those offsets were stable. And so I think that does bode well for being able to work around those issues, and we are documenting now, and hopefully we'll be able to put out B1 calibrated data sets in the next few months. Next slide. In addition to the data streams themselves, there's also a wave of products that will come along, and translators such as myself will often be responsible for producing data products. Some of the initial wave of ship-based type products are already available. So things like interpolated sonde or PBL height from the radio sondes are already there. MWR red, I think in an initial form, is also available. MPL cloud mask. A few of our school is one that I will get to in a bit as well, but a lot of the initial wave of products are there. Typically ship-based deployments do not have as many core products, but I think MOSAiC is an exception because I think, especially with some of the new translators like Damao and Jian coming on board, we'll have additional waves of products, and that will include some expansion into microphysical type retrievals. So these are things like microbase style cloud property retrievals, cloud optical depth from the photometer should potentially be possible, as well as cloud phase from like Shupe et al. Type methodologies, ARIOE, and additional ways of getting PBL height from other instruments. So I think, though not all of the products are available now, they will be forthcoming. And I think it's kind of exciting that there will be such a complement. And certainly you can reach out to Damao as the translator point of contact for more information, or the specific translator if there's a product in particular that you think that you'd be interested in having access to, because we can probably give you up to the minute details on when it's available or will be. Next slide. So yeah, as I said, one of the things that we were, at least on our Brookhaven side on our team, we tried to do was to make sure that we had a few of our sort of signature products available for this meeting. One of them is RSchool. RSchool is kind of an interesting opportunity here, because it is, as I said, it is one of the few times where we have both vertically pointing systems of a K-band and a W-band, so we can do some cross comparisons and see just how sensitive we have been or how the radars perform for some of these cloud boundary detections. But overall, we're fairly happy with this. I will also note this as an opportunity to say that sometimes we'll release products as evaluation. That does not necessarily mean it's bad. It's usually just like the 95th percentile step in the product chain. It means we are just working through some nuances of a campaign. But I would say, you know, certainly feel free to download, look at these products, give us feedback, because then we will probably, once we have final B1 calibration, release a final release of this. But for the most part, these are completely workable. And I think we're really excited that these data are there and they're available for people to download. So as I said, have at it, and by all means, feel free to give us feedback as best you can by looking into these types of products. Next slide. So sort of final two slides, I'll give a plug for us on the translator side. I said I'm filling in today for Damao Zhang, who's in another session, but he's the MOSAiC point of contact. We are one of the points of reference within this program. If you have any issues with data products, if you think that there's a product that we should be doing that's possible, you know, please let us know, email, contact us. If you have PI products or other things that you think would be of interest to the community, we can also work with you to get your PI products up with the ADC and getting DOIs and other things. So I think we're a resource there to help you, especially if you can't find data that you think is supposed to be there, or if you're interested in potentially certain types of products that you think we should be doing. Certainly feel free to contact any one of us you see there, including myself. Next line. And finally, sort of as a concluding slide, we'll say that every data set that I spoke about today, if not now, at some point in the future, will be available through ARM's data discovery tool. It has gone through some changes in its interface a little bit if you haven't been there in a while. Most of the questions that I typically field as a translator often relate to, I can't find a particular data set, and it usually is not because it's not there. It's often just toggling a button or just knowing the particular naming of the instrument or the type of sensor that we're looking at. So more often than not, we can resolve those types of issues fairly quickly. A few things that I will point out is most of the people on this telecon will most likely be looking at B level or C level data, usually your mentor quality control or product level data in sort of the ARM terminology. And then finally, and then I'll say as a last point, a lot of PIs still don't know about the availability of the ARM Quick Looks data browser. I have a link up there on the screen, sort of the second bullet, but that's also a very good reference for you if hunting for events and you're just trying to see. There's a pretty good correspondence between, if you see it on that data browser, it's also on the archive. So it's a good chance to just type in a range of dates, specific instruments or multiple instruments, and get a couple of quick looks to get a good feeling of cases. And as I said, a lot of users are still not even aware that that exists. So I always like to point that out. And again, if you miss the link or can't copy this or get into a Google search, you usually type that in, but otherwise I can always provide that link to you in the future. But it is a nice resource to have if you're really just interested in diving into some of the data sets. But with that, that's my speech. I'll see to any other time I have.
Thanks, Scott. I'll just say really impressive. I mean, thanks to you and the whole ARM apparatus. I mean, it's really extraordinary how the process works. And, you know, MOSAiC was a big challenge in many ways, and still the system worked. And I think that really just, you know, it illustrates how effective this multi-year ARM activity has been to develop all these mentors and people working on data at different levels. It really is very effective. And I will say it's really a point of pride for myself, working with this huge international group of people, to be able to tell people go look at the archive, data discovery. There it is right there, right? Because most people's data is not available, right? So the fact that ARM data is available is really, I think, a point of pride for DOE and the whole ARM apparatus. So thanks to you and everybody for all the work you guys put into making sure that that's the case. Let's open for any questions that people might have for Scott.
Looks like we've got several hands raised, Matt.
Okay, yeah. I'm not seeing those. Whose hands are raised?
Matt, mine is, but we have a couple others. So Mark or Bikey, if you guys want to go ahead.
Yes.
Yeah, go. Feel free to ask your questions.
Oh, okay. I just curious because you said the article will available, but I look at your page 11, the top panel. If you can go to that, the top panel, you have a cloud. There's no radar reflectivity. I believe you probably have some other instrument you can see the cloud top at 0Z to 2Z. Look at the radar reflectivity and the black dots, and you get a much higher cloud top in the top panel. Is that other instrument can look at the cloud top by ARM?
Yes, so our school is a multi-sensor approach. It does take in the MPL, it does take in the radar, it does take in radiosonde. So yes, it's not exclusive to just the radar echoes as far as where it derives its cloud boundaries. But so yeah.
Yeah, I think I understand you get multi-instrument. However, if for the micropulse LiDAR, they cannot penetrate that thick cloud. That's, I believe, how you see the cloud top from 0 to 2 if over here. And the other thing is, do you think from 18Z to 24Z, your cloud boundary is near the surface? And is that the bottom reflectivity is not cloud, or?
So I guess in the case of, so going through just a step through that quickly, I say we could certainly discuss any of the cloud boundaries, but I do think like from the LiDARs, there was some fog and some other persistent thing that I've been aware of in terms of some echoes that would come in at very low levels. Separately for some of the cloud boundaries as well. One of the things for this particular R school implementation is that we only were showing the reflectivity from the general mode of the Kaiser and not the complete reflectivity field because of the artifacts that I mentioned with the MD mode. So some of the discrepancy as far as availability of reflectivity may very well be that we trusted the Kaiser for cloud boundaries, but not necessarily to display reflectivity at this time, given that offset because of the issues with that pulse compression filter. So my guess is in this particular instance, that's one of those cases where we just are not showing the reflectivity there because we didn't have confidence in it as sort of a best estimate.
Oh, I see.
Answer that.
Thank you.
I think Mark was next. Oh,
yeah, thank you very much. And I apologize for asking a question that maybe you already provided an answer early on, but I wasn't here. So first of all, thanks a lot for this presentation and the amazing work. These guys is amazing. So it really just makes us, yeah, we're thankful for all this massive data set there for us to play with. The question I have for you is like, it's not fully clear to me, and again, maybe it's already said, is the data set that you guys are talking here, is that data set only collected or related to instrumentation from ARM, or is the data set from MOSAiC as a whole experiment available through ARM, the same web page, or one has to go fish instrument by instrument through all the different links and institutions that participated in MOSAiC?
I'll let Matt answer that one for the rest, but I was exclusive to ARM in my presentation, but for the rest of it, Matt, by all means.
That's a great question. MOSAiC is a complicated international endeavor, right? So there is data. There are data in many archives. The Pangea archive in Germany is the kind of primary home for MOSAiC data. And so a lot of data is there or will be there. And there are a few other archives, the ARM archive being one, that are basically confirmed as partner archives for MOSAiC. And so those are all kind of linked. The MOSAiC data policy, though, has it that data does not have to be publicly available until the 1st of January 2023. And so a lot of individual investigators' data is not available yet and won't be for a while. And that's where, again, I'll just heap some praise on ARM, because ARM makes their data available right away. And I think that enables and brings more people into science. And so, yeah, if you really want other MOSAiC data, you do have to look at Pangea or some other resources. I can help people out if they're interested in that. One thing that I have negotiated is that anybody that's funded by DOE can be part of the MOSAiC consortium, which gives them access to all the data before it's publicly released. That's just one benefit. It took a little negotiation, but that's something. So, if you get ASR funding to do science, then you can have access to all that other data. Otherwise, you either have to address individual PIs to get that data or wait until it's publicly available. And that's just part of the deal with how we were able to negotiate our data agreements.
Thank you very much.
Laura?
Yeah, I wanted to comment to Scott's presentation that I was very excited with the ARM data set, in particular, the fact that I think for the first time, as far as I know, we've gotten some scanning radar data to look at spatial structures in the clouds and possibly cloud dynamics over this Arctic sea ice. So that was really a great accomplishment for MOSAiC. Obviously, I was disappointed with the failure of the X-band radar, but I have been trying to look at some of the KSACR data, and I'm getting a feedback. You showed that there's a lot of availability for the KSACR, and that's great. But when I tried to go to the data set, I got the message that it was under reprocessing, and I was curious if you had any comment about what was going on there.
Well, as far as I'm aware, so our team is in the process of putting through additional gridded SACR products that should be available soon. We also need to adjust for the ship correction of it, because it's, the ship will be tilted maybe by a degree or two, so we have to offset for that. We can certainly take this offline if you can give me the specific message, and we can go over it, because I do believe the data should be available there, except there may be some gaps in some areas, but I'm fairly confident most of the data should be there. So I guess in that sense, it may be easier just to
okay, we'll take it offline.
Okay, Scott, I have one question that I'm sure some folks on this call will be interested in. So for the aerosol measurements, obviously there was the huge issue of the ship contamination and contamination from the snow machines and the vents. And there is a broader MOSAiC effort to come up with some sort of maybe multifaceted pollution flag so that users are aware of what periods and what measurements might be affected. Is there one for ARM that specifically you guys are developing? I know there's the purge flag, but that's not the only metric for when pollution was affecting the aerosol measurements. So is there any sort of effort that ARM is going to put forward to kind of develop a more detailed flag for the local contamination on the aerosol measurements?
There's none that I'm aware of, but that doesn't necessarily mean that I can't raise that with both John Schilling and several others in order to establish that. So I can certainly make a note of that and get back to you and the rest of this team as if for anyone who may be interested in that.
Great, thank you.
Great, thanks for those questions, everybody. Questions really help make things go nicer. It helps to fill in a lot of the details that we didn't get to otherwise. So now I'd like to turn things over to Michael Gallagher, and I'm going to pull up his presentation here to talk about a merged data product. Michael, why don't you take it away? And I'm not hearing your voice, Michael. Still not hearing your voice. Let's see. I wonder if you can maybe work on that and we can move ahead with some other science presentations and we'll come back to you. All right, sorry about that, everybody. We'll try to work on those issues, but let's move into our Science Bites section. So this is where many of you all have provided some slides. So we'll start out with, I believe is Xianda going to present, or is?
Yeah, I'm here.
Jian?
I can start.
Xianda, okay, I'll hand it off to you guys.
Yeah, can you hear me okay?
Yes.
Okay, so I'm Xianda from Washington University in St. Louis. We are evaluating the data from the MOSAiC campaign. We focus on the aerosol in general and system and particle hydroscopicity in particular. So as Matt already mentioned earlier, so we have some pollution during the MOSAiC campaign. And the first step for us, of course, is to terrorize the pollution and get rid of the pollution. We care about the natural process and their feedback to the aerosol at this end. So from these figures, you can see we plot different parameters such as temperature, pressure, wind speed, and also total particle number concentration, and also the fluctuation of the total particle number concentration on the right, and also the counterplot of particle number size distribution. Based on this, we terrorize the pollution by our eyes. So we think our eyes is a very good tool to pick up the pollution. It is very time consuming, but it's very precisely. So as you can see from the counterplot on the right panel, maybe from roughly 8 o'clock on 26th of August, you can see that there are a lot of smaller particles. At the same time, on the upper panel, you can see the fluctuation of total particle number concentration goes very high. So we assume this is the pollution directly from the chimney. And also, before you can see start from earlier 25th of August, there was a new particle formation event were observed. At the same time, you can also see there are some noisy side distribution, the noise signal in the side distribution, and the standard deviation of particle number side distribution also shows small fluctuation. We assume this might be someone work on the cross-stack work on the ice flow. They may also generate some pollutions, and we will pick up this different pollution periods. And in the lower panel, you can see after cleaning how the particle number size distribution counterplot looks like. So based on our eye detection, we pick up all the pollution events. There is another group from EPFL. They are also working on different methods. They use statistical analysis tool and also machine learning algorithms. We are comparing with our results. Evo from the EPFL, he was taking off the comparison. We will have a technical paper to describe our method concerning the pollution characterization. Can you go to the next slide? Yeah, after cleaning the after cleaning the pollution, we have a nice particle number size distribution. Here I show the monthly variation of the particle number size distribution in the Arctic. As you can see from the March, April, and May, you can see a very high concentration of the accumulation mode. This is due to the Arctic haze, like the pollution, a long-run transport pollution from the south to the central Arctic. And start from the summertime due to the more precursors from the ocean and also the sunlight, you can see there are some neutron formation event happens. Therefore, we had a lot of newly formed particles. You can see there are strong concentration from Eskimo particles. This measurement from spring and summer are quite comparable to previous studies. They also have this size distribution measurement in some locations around Arctic. But one surprising thing is you can see from the November to January, we also get very high concentration and also a broad distribution of target number size distribution. This might be due to the snowstorm. We observe a very high concentration of the cosmos particles, and also at the same time, we also see very high concentration of Atkin and accumulation mode particles. It might be very interesting to see the snowstorm not only contribute to the larger size particles, but also contribute to the smaller particles. Yeah, and also we are also evaluating the cloud concentration nuclei number concentration and particle hydroscopicity property. This data are all ready, but due to the limit of time, I just stop here. Yeah.
Great, thank you very much. I see that Jessie raised your hand. If you have very short questions here, we can do them. So why don't you do that while I get the next work?
Yes, mine is short. Nice work, Xianda. So are you guys going to make this available as a PI product through ARM?
Yes, yeah,
Okay.
sure. Yeah.
Cool. Excellent.
Can you hear me now?
Yes,
Yeah.
Michael, we can hear you now, but we'll take yours at the end.
That's great.
And I'll fit in nicely. So next up then would be Jessie talking about INPs.
All right, so I'm one of those people that gave a lot of slides, but hopefully won't spend a lot of time. So I'll talk a little bit about the INP measurements that we made during MOSAiC for the full year. So next slide. So some of our targeted objectives and questions were to really improve the understanding of the sources, efficiency, and the abundance of INPs in Central Arctic for a full year. Next. And so we have some targeted questions, mostly focused around what local sources could contribute to the Central Arctic INP cycle. So how do the seasonal changes in sea ice and air mass influence INPs? Is marine and sea ice biology a significant source of these versus terrestrial sources from distal regions? And are leads and melt ponds viable sources of INPs, and do they exchange the atmosphere? So next slide. So basically how we did this is we had thousands of discrete samples collected during the expedition. So we collected daily aerosol samples that were total and size resolved. We had an aerosol sampler that went on to the ice to collect near leads and melt ponds. And then we had collection of seawater, sea ice, and snow samples to look at the potential linkages with local sources. So next. And so we take a subset of these samples and we use a couple of different techniques to look at immersion freezing ice nucleating particles, or INPs. So we do that in addition to looking at DNA sequencing of the aerosol samples to look at the microbial identification of some of these possible INP sources. Next. And so I'll just give a little blip of the annual cycle of the INPs that we observe. So these are looking at different temperatures where INPs start to form ice at. And so at the top of the plot, that's where some of the warmest temperature INPs kick in. And then as you go down into the graph, that's where some of the colder temperature INPs kick in. So the top would be mostly indicative of biology or biological sources of INPs. And then as you get to the colder temperatures, that's where things like mineral dust and other sorts of microbial things can actually serve as INPs. And so next, sorry, I have a lot of animations. So you can see that there's a pretty unique seasonal cycle of the ice nucleating particles. And so during the fall freeze up, we really don't see a lot of these INPs present. As the start of the Arctic haze kicks in, so starting in about January into the spring, that's where we see some influences from colder temperature INPs, which could be a sign of dust influencing the sites. As we have the start of the melt season, so in May that Matt had mentioned earlier, that's where we start to see a little bit of those warm temperature INPs kick in. And then at the peak of the melt season, where we have biological productivity that's most active in the Central Arctic, that's really where we start to see the largest concentrations of these really warm temperature INPs. And so next slide. And so I have a lot more details on my poster, which is later on this afternoon. So if you want to find out more, we're seeing some really unique trends with the sizes of the INPs and also different treatments that we apply to the samples to look at the biological and organic containing INPs. So we're hopefully going to be submitting a paper on the INP annual cycle this year. And I want to note that our INP and DNA data will be available on the ARM Data Archive this summer, and actually, hopefully by the end of this month, end of July. So please feel free to use our data. We're happy to help with interpretation of the data, and we would love to see people actually using these data. And so we'd also like to thank, Dewey and ARM for funding this work, and then NSF and Alfred Wegener Institute for supporting travel and logistics.
Great. Any quick questions for Jessie? We can definitely entertain more detailed questions later as well. Next up would be Kerri Pratt. Take it away, Kerri.
Hello. I'm hearing a lot of background noise. So we collected next to Jessie's aerosol sampler, we had a rotating drum impactor with 3 stages, so very similar to Jessie's collection technique, and collected daily samples on 3 stages for the majority of MOSAiC, except for that short time period, I think in February, that Jessie doesn't have data for as well. And as soon as we get facility access, which we're hoping to later this summer, we've been limited due to COVID. But as soon as we get microscopy facility access, then we'll be doing computer-controlled scanning electron microscopy with energy dispersive X-ray spectroscopy. So what this will give us is individual particle size, morphology, and elemental composition. So this will allow us to distinguish the mixing states and sources of particles. So on the right here, I've shown an example of some of the types of data that we can get. This is number fraction of particles versus particle diameter. And so this is for winter time near Okayavik, near the ARM site in Alaska, showing organic sulfate particles at the lower sizes, but sea spray aerosol observed even in the wintertime due to the leads present. And we've connected the organics on those particles to the leads and the lead microbiology. And so I've shown some other examples here of references here. If you're interested in that type of data, we're happy to collaborate with folks on this. Thank you.
Thanks, Kerri. Are there any quick questions for Kerri? Okay, next up, Hannes Griesche.
Yeah, hi everyone. I'd like to present you our activities towards a data set of Arctic cloud microphysical properties, which we are going to provide. And you can also already go to the next slide. In order to do so, we combine different remote sensing instrumentation, like the Cloud Radar Quasar operated by ARM, together with some instruments we had in our own container, 2 microwave radiometers, 1 HAPRO, and also the MOSAiC passive, which is sensible for lower liquid water contents, a distrometer, and multi-wavelength LiDAR. And these measurements we're going to process synergistically with the CloudNet processing chain to get the profiles of cloud properties, like cloud boundaries, phase partitioning, the liquid and ice water content, and effective radii and turbulence. And by means of our LiDAR, we also can get cloud and aerosol properties due to our multi-wavelength capabilities, the environment capabilities, and due to multiple field of views we had to get like something like the cloud droplet number concentrations. And then next slide. And to account for the high variability of the clouds in the Arctic, especially to account for the very low clouds, our plan is to get 2 data sets of the CloudNet chain, one for the very low clouds, using the near field of the LiDAR poly-XT together with the Kaiser general mode, and then one for the higher clouds using the poly far field and the Kaiser moderate sensitivity mode. And here we noticed this offset, which was also mentioned earlier, between the two modes, and this is why we haven't done this data set yet, and we would like to calibrate the Kaiser data. So if any one of you can provide us with the CloudSet reflectivity for summer 2020, we would be very happy. And yeah, to address Mark's question earlier, so once we are happy with the reflectivities of the Kaiser and we have done our data sets, this will be published via Pangea. So that's all from my side.
Great. Are there any questions for Hannes? I will just make a statement that this is really, I would say, a great success story is to seeing, you know, Hannes, you're from Germany, or the Tropos Institute, and it's really great to see this collaboration internationally happening. This is something that I know in ARM that, you know, we certainly have envisioned for many years to develop some of these collaborations, and I think MOSAiC's an awesome opportunity to really build some of those. So it's great to see you all involved in using ARM data, and we certainly want to do anything we can to help make sure you guys can continue using that data. So thanks for your
time. And I definitely agree.
Cool, great. Okay, next up is me, and I'm going to talk a little bit about cloud atmosphere impacts on the surface energy budget. And so there's a poster on this that you can look at. Some of the project goals here are to characterize the annual cycle of the surface energy budget and to look at the kind of seasonal effects on the partitioning of that energy budget, and to really kind of put these observations out of the sea ice into the general concept that we've been establishing across the Arctic and under a variety of conditions and at a variety of sites, including northern Alaska, including over sea ice, including over Greenland, and how can we put together this whole puzzle to understand conceptually how clouds impact the surface energy budget, and then of course how can we represent that in models. So pretty much one result slide. Up in the upper left, this is distributions of net long wave radiation. We see the cloudy and the clear states. We've known about this for a long time, of course. At many sites, you get these two different cloudy states of the Arctic, or two different states of the Arctic kind of radiative system. One in which there are clouds, typically liquid clouds, one in which there are not those liquid water clouds. But those states actually drive the other energy balances at the surface. And so in the bottom panel, what we see, we take the net long wave radiation on the y-axis, and these are just raster plots, kind of PDFs, two-dimensional PDFs, showing relationships with things like the subsurface heat flux, or the sensible heat flux, or the near surface temperature gradient, which is related to sensible heat flux. And you see these nice distinctions between the cloudy state, which is near the top, circled in red there, and this kind of clear sky state, circled in blue. So driven by these two different long wave radiative states, you see changes in these other important energy terms. And so we want to look at a variety of relationships here and really understand these relationships and some of the sensitivities and influences, so we can develop a kind of conceptual understanding. And so this is really approximate for the winter time at MOSAiC. You know, you have the balances of energy on the left side in the clear sky, and I haven't put any numbers there, just all the arrows showing you have long wave cooling from the surface, you have some amount of downwelling long wave from the atmosphere, you have warming of the surface by turbulent heat fluxes, and warming of the surface from conduction from below. Now you add a cloud to that, and there are some significant changes. You see in terms of the net long wave radiation, you see an additional 35 watts per meter squared at the surface. You also see that the turbulent, sensible, and latent heat fluxes are decreasing, and they become pretty neutral near the surface. And you see a modulation of the conductive heat flux from the warm ocean below up towards the surface, in large part, oops, sorry about that, in large part because of the change in surface temperature at the time. And so you see some conceptual temperatures in the center panel here, where the Bottom of the ice temperature stays about the same, but the top changes between these cloudy and clear sky states, and that affects the thermal structure of the ice, as I showed us in the earlier plots. So these are just kind of real approximate conceptual understanding right now. There are a lot of important sensitivities like the depth of the snow that really affects things like how much the conduction of heat through the ice from the ocean relates to the surface temperature and the emission at the surface. And so all those pieces we want to dive into, understand the role of snow depth, the role of ice thickness, and other processes in how these energy terms are partitioned. So that's it for me. Any questions that people have about that? Okay, next I'd like to bring up Sergey Matrosov. There we go, precipitation.
Can you hear me?
Yes.
Yeah, so MOSAiC data provides some significant potential to improve on our knowledge of Arctic snowfall and microphysical processes that govern it. And my couple of slides are about the planned activities of snowfall studies using MOSAiC data. As you know, there were a number of different gauges, dendrometers, optical sensors deployed at the ice camp and on the board of the ship. And there were a number of radars, which we heard about today, which measurements can be used for the snowfall parameter retrievals, and there were measurements on snow on the ground. The first activity, which is a very important one, will be to critically analyze the data from different sensors. And the challenges for that activity, you can see on the left frame of this view graph, which shows snow accumulation during the months of November from different sensors from MOSAiC. And obviously there is some significant variability, those sensors readings. And Kaiser data are most consistent ones, which are in terms of data availability. And an example of the Kaiser measurements of a snowfall event was shown on the middle frame of this view graph, which happened to be a measurements during the November 15th, 2019, when an Arctic cyclone passed over the MOSAiC site. And the right frame of this view graph shows retrievals of the liquid equivalent of precipitation rate from two sources. Kaiser data retrievals are shown by red dots at a height of 160 meters above the ground, and the green dots show the results from the optical sensor, Weissel optical sensor on the ship. During periods when the snowfall was more substantial, between 22 and 24 hours, the agreement is good, as you can see. However, during some other periods, like at 10 o'clock, when the radars saw cloudless sky, the optical sensor was indicating some significant snowfall, which is probably an artifact due to blowing snow. So an important activity would be developing a high temporal resolution MOSAiC snowfall rate product with estimate of uncertainties, and probably the central piece of this would be retrievals from the radar measurements, but also some normalizing of radar retrievals will be used from the other sensors when during the periods when those measurements from those sensors are available and reliable. And the next slide, please. And using this unified product about snowfall rates during MOSAiC will allow us to study process of a snowfall and their influences on snowfall rates and microphysical parameters such as characteristic size of the particles, snowflakes, ice water contents, snowflake shapes. And the most important parameters we are planning to look at are those rhyming, aggregation, secondary ice production, and a couple of the cross sections here show some early measurements from Rector Point, Alaska, indicating how vertically pointing radar measurements of the moments can be used to distinguish between different mechanisms of snowflake growth, like aggregates, mostly dry aggregates, and graupel, which is an extreme example of snowflake rhyming. Those two mechanisms in reflectivities look similar, so the graupel with more dense graupel and large aggregates produce similar reflectivities. However, if you look at the Doppler velocities, we can distinguish between two this mechanism, more dense graupel falling faster than aggregates. And another activity which is very important is refining those remote sensing approaches to identify different snowfall microphysical processes with inclusion of dual wavelength measurements from AIM-Wacker and Kaiser, and also polarimetric measurements from the K-Sucker. And I guess I'm done here.
Okay, any quick questions for Sergey? Okay, we'll move on to your person. Here we go.
Okay, so our project tries to look at the dynamic and thermodynamic impacts on the sea ice from both synoptic and mesoscale events. And so the general hypothesis is that both kinematic and thermodynamic, or dynamic and thermodynamic, atmospheric impacts on the sea ice are associated with synoptic and mesoscale features and processes, and are hence modulated by this temporal variability associated with these. In particular, we're hypothesizing that ice translation is primarily driven by low-level winds. So the temporal and spatial variability of these winds strongly impact ice movement and deformation. Also, that two processes drive ice deformation, and that is the lower atmospheric deformation itself and the strong winds occurring over area of spatial gradients in surface roughness, or spatial gradients in surface drag. And finally, that the variations in the large thermodynamic cloud forcing of sea ice strongly is modulated by synoptic and mesoscale dynamic forcing of cloud and macro and microstructure. So we're exploring this with the MOSAiC data set, and the preliminary results are that we have identified some of these events when we have these interactions. Primarily, we started by looking at the dynamic air-ice interactions. We haven't gotten too far yet with the thermodynamic interactions, but we have seen that the interactions are definitely both dynamic and thermodynamic in nature. For the dynamic air-ice interactions, we've been trying to look at, use the distributed network sites, the position buoys, the GPS buoys in particular, to identify some of the ice dynamic events. And so you can see that to the left, a diagram of the different buoys. This was in early November of 2019, it's the locations. And the black ones are the GPS buoys, the green ones are these snow buoys, and the blue ones are these ELS sites. They all have GPS involved with them, so we can look at their movements and get some ice dynamic calculations from that. So in the lower right, you see here the time series of an area change. So you choose a triad, so 3 of these buoys, and then you calculate in this case, an area change is what's being shown here. You can see how episodic that was, especially during most of the winter, and then towards the spring, it almost starts becoming almost continuous, these dynamic events. So right now we're looking primarily during the winter time period. And we've looked at particular 2 case studies mid-November, they're labeled with A, and right around February 1st labeled with B. For the atmospheric deformation or divergence calculations, we use these L sites with these sleds. You can see in lower left, yes, berries are attacking it at that time, but those are the sleds that we were using. And so we're calculating atmospheric divergence from this. So now this plot I'm showing here in the middle of the diagram, L1, L2, and L3, shows the winds concurrently at those 3 sites. And you can see that there's a very sharp change in wind speed and direction across the distributed network. So this is this February 1st case. We had some very strong, sharp changes going across the network. Next slide, please.
And I'll say that you're already at 4 minutes.
Oh, okay. So very briefly. Next slide. Yeah. So we're doing all kinds of deformation calculations and with the ice, and then looking at the atmospheric measurements and also including model output, which is in the right slide there. I won't spend too much time. This is on the February 1st case. Next, please. And then one of the things we're seeing, this is again the February 1st case, one of the things we're seeing is that it's connected, some of these mesoscale features in the atmosphere are connected with these dynamic events in the sea ice. So for instance, in the bottom time series there, the bottom panel, we see both the atmospheric divergence, which is calculated in red there, and the ice divergence and ice shear actually in green and blue lines. You can see how they maximize in amplitude there right around 2Z on February 1st. And this is the time when we had the minimum in sea level pressure with the cyclone, and it was right over top of the MOSAiC area. And there was a dual low-level jet feature with this cyclone. So strong winds from the southwest changed very quickly over to very strong winds from the north-northwest or north-northeast. And so there was so if the ice is moving with the low-level winds, there's very rapid changes in the ice motion. And so this is why the ice divergence and shearing and so on is going on there. And it's a mesoscale feature associated typically with Arctic cyclones. And so we're seeing that a lot of these ice events are mesoscale features and often associated with cyclones, but not always. So I'll just leave it at that.
Great, thanks, Ula. Complex study. You've got a lot of information there already, I see. We'll move on to HICE to give a little insight into uncrewed aircraft systems.
All right, yeah, thanks, Matt. Good afternoon, everyone. Hopefully you can hear me okay. Got the edge of a stable internet connection here. I'll give a quick update on the UAS activities we conducted during MOSAiC through some funding from the National Science Foundation. This was a team from the University of Colorado, along with some European collaborators of opportunity. Next slide, please. So Matt gave a nice overview of MOSAiC. One more click, Matt, please. I'll show where we actually operated. We were connected with legs 3 and 4 during the cruise, and the green dots represent locations where we conduct Datahawk flights, the red dots where we conducted Helix flights. I'll talk about both of those platforms in a second. With a little bit of careful planning and testing, we were able to operate successfully up to about 87 north. Matt, next slide. So the Datahawk is a platform that the ARM community is fairly familiar with. It's operated at Lichtock Point and other sites. We leverage this platform to complete a lot of profiling out over the sea ice. You can see on the top right, a lot of thermodynamic profiles that we collected during 2 legs. You see a lot of familiar features if you're used to looking at the Arctic atmosphere, both surface and elevated inversions. We're leveraging these data to conduct a variety of studies. Gina Joseph from our team has started looking at characterizing boundary layer properties and depths and things like that. And we're also looking at leads and their impact on the atmosphere with some of these data. Next slide, please. The second platform is the Helix. This is a hexacopter that was instrumented with gimbaled pyranometers, so we can do surface albedo surveys as well as collect surface imagery. can see some of the products that we collected along the way. We did gridded surveys of ice albedo, as shown in the middle there, as well as kind of detailed hover over different surface types in the top right, and profiling to understand how spatial heterogeneity in the ice surface impacts the albedo measured at any given altitude. And last slide, Matt. So data is a big topic. Of course, we're in the process of finalizing the quality control on our data sets. I think for the Helix, we're all set, and we're putting final touches on the DataHawk data. We hope to have those data on the NSF Arctic Data Center archive by the end of the summer. And you see the list of scientific areas of interest that we're going to move forward with. So thanks.
Thanks, Heis. Are there any questions for Heis about the UAS activities? Okay, Amy Solomon and some model work. Amy, take it away.
Can you hear me okay?
Yes.
Okay. So this is on a project, we're calling it the MOSAiC Near Real-Time Verification Project, because we were providing forecasts to the campaign to support the scientists by providing forecasts of surface conditions, the snow and the ice, and the structure of the atmospheric boundary layer. But we've transitioned to using the observations from MOSAiC to evaluate short-term forecasts of the coupled system. And I'm going to talk a little bit about our first project, which is using the wintertime statistics. And we're using these observations to evaluate some of the coupled processes that are unique to the Arctic, such as the representation of liquid-bearing clouds at cold temperatures, the representation of a persistent stable boundary layer, how snow layers limit the impact of atmospheric variability on sea ice, and ocean sea ice atmosphere coupling. And we're using the short-term forecast because we want to identify potential errors in the representation of fast processes, such as cloud feedbacks and surface fluxes. And we're designing process diagnostics using observations of the snow in the sea ice from the ice mass buoys, the atmospheric structure from the soundings, the cloud characteristics from the radars and the LiDARs, and the surface fluxes from the 3 separate flux stations, 10 to 20 kilometers from the central observatory, and the 23-meter tower at the observatory, at the central observatory. Next slide, please. So I just wanted to show some of the results that we have so far from the study. This slide is showing the scaled sensible heat flux. That's the 2-meter sensible heat flux divided by the wind speed relative to the near surface stratification. And if you look at the upper left, so these are the observations from the flux stations. Each black dot is a 10-minute average. And then the red dots are half-degree bins with the flux stations bins separately. So there are 3 dots in the vertical in the red. And so what this shows is that for cloudy skies, which is the negative stratification, we're getting scaled sensible heat fluxes from about 5 to 10, which decreases as the stratification decreases, and then goes negative as the stratification becomes positive. But what's really interesting is that as the stratification becomes larger, the sensible heat fluxes decrease and then go to 0. So that's saying that for very stably stratified cases, the turbulence is shut off. And this is something that was observed during Sheba and other wintertime campaigns. So I'm just showing a few examples. So these are 3 of the forecast systems. We have 9 different forecast systems in the study right now. But the upper right, forecast system A, is the only model that is able to simulate the maintenance of liquid in clouds at very cold temperatures. So you can see that it's able to simulate this distribution for negative stratification quite well. And it also is able to simulate the decrease in the turbulence as the stratification becomes positive. But if you look at forecast system A and forecast system B in the lower left, both of these models simulate the reduction in turbulence for stratified cases, but they both do not simulate highly stratified cases. So even though both of these models include similarity functions based on the observations from Sheba, that's the damping of turbulence for stratified cases, they both are not able to simulate very stably stratified cases. Forecast system C, you can see, is a straight line, which means that it has a constant in its transfer coefficient for the parameterization of the sensible heat fluxes, which means that as the air gets more and more stable, the fluxes get larger and larger, but this is the only forecast system of these three that can simulate these highly stratified cases. So these are some of the interesting results that we're digging into. We're collecting the parameterizations used in the different models to understand what's causing these biases and how to improve them. Next slide, please. So I just want to say a little bit about another project we're working on. It's called the MOSAiC project. So we're developing an integrated data set of the coupled Arctic boundary layer. So that's from the ocean mixed layer through the sea ice and snow to the atmospheric boundary layer. And it's designed specifically to evaluate Earth system models. So how to use point observations for the MOSAiC campaign to evaluate these relationships, like what I showed in the previous slide, and the different terms in fundamental equations like the surface energy balance. And so that's in progress, and we will be submitting this data set for the Earth system model community to use after the fundamental data sets, the data publications have been submitted. So thank you.
Thanks, Amy. Any questions for Amy? Okay, and Michael, I believe that you are able to be heard now, I hope.
Yeah, I think so. Can you hear me now?
Back up with yours. So another data set. Take it away,
Sure.
Michael.
Great. Is that slide one? Yes. No.
There we go. Sorry.
There we go. That's better. All right. So my name is Michael Gallagher. I'm a researcher at the University of Colorado studying atmospheric transport, surface processes, and coupled systems. I was out on MOSAiC in the midwinter on leg 2, and then again in the late summer on leg 5. It's really great to see a lot of people here from MOSAiC in the chat list there, but it's even better to see lots of people who weren't out on MOSAiC, lots of people interested in the data sets, and lots of people interested in just the wide range of observations that are available out there. A lot of my work right now and a lot of the work of the people on my team here at the University of Colorado is to create a merged MOSAiC data product. So to take it a step further than just taking the observations, which is the hard job, we now have the second hardest job, which is analyzing the data and aggregating it in a way that's actually useful. And this is kind of tied to the question that Mark asked, which is, how do you actually get these data sets? If you didn't go out there, if you're not a PI on a project, how do you go out and you aggregate all of the different things you need to do atmospheric systems research? And the answer ideally is that someone who knows the observations does it and aggregates it in a way that makes it useful to you. That's what I'm trying to do. So system science research, of course, takes a diverse, incongruous range of in situ observations, and it takes all sorts of different types of observations, right? You have vertical atmospheric profiles, you have low cadence observations at the surface of the ice sheet, and they're made by a whole bunch of different institutions, a whole bunch of different PIs, and a whole bunch of different projects. So our goal is to take all of those different things and to aggregate them together. I've been working with individual mentors, and Matt Shupe has also been working very closely with ARM and DOE on making sure that we can aggregate these observations in a way that respects the contributions of all of the people that were out there on the ice sheet and all of the people who spent years of their lives making sure these great data sets were taken and useful. So we're going to try to create this data product with concern for institutional and contributor attribution, but even more so, in my opinion, from a science perspective, the most important thing is to do it in a transparent and documented way. If you're a scientist, you're trying to use observations, you have to trust that I and our team is creating this data set using observations in a way that respects the kind of fickle nature of taking observations out in the Arctic. And maybe the final / most important point is the standardized file semantics and conventions. So this is in conjunction with YOP SiteMIP, which is a much broader project that is trying to standardize Arctic data sets in a way that if you want to ask science questions of all of these different super sites in the Arctic, you can aggregate the observations from those sites in a standard way. Next slide, Matt. Great, so this is a meeting where we've come together to understand and discuss atmospheric systems research. And the only way to do that is to combine these data sets into a comprehensive picture. And just to give you a flavor of what that will look like, we're starting, I'm an atmospheric scientist, so we're kind of starting from an atmospheric science perspective. So aggregating vertical atmospheric profiles from arm instrumentation on the bow of the ship, including radiosondes and including derived products. So Hannes gave a great overview of what they're trying to do at Tropos. Ideally, we're going to be working with them to also integrate their product along with what the observations that our team took on the ice sheet. So I was part of the flux team in MOSAiC, and we focused on taking flux observations at the surface, out at Met City, and at these remote sites that everybody has mentioned. And so surface fluxes such as radiation, turbulence, energy, and momentum fluxes calculated from those turbulent parameters are all going to be in the data product. Atmosphere-snow interaction is going to be emphasized from a science perspective. So how do you take this atmospheric system and couple it to what a lot of people care about, which is the snow and the sea ice? And then kind of one of the longer range goals is, of course, to do a fully coupled climate system. Of course, there are all sorts of great observations, buoys that go down below the surface, take profiles through the ice, and then down into the turbulence of the ocean to measure the turbulent profile in the ocean. And we would really like to have a fully coupled climate system data set. And this is initially geared towards model evaluation. The goal of the OpSiteMIP is to evaluate these processes, and in particular, just to do process studies to understand models, similar to what Amy Solomon was talking about just before. But also, my personal goal is to make the observations available to process studies to scientists who are interested in all sorts of things. So it's in one merged data set. It's in something where you can go and you can trust that these things have been aggregated from the instruments in a way that respects the observations. Next slide, Matt. Great, so just some detailed information. I'm skimping on a lot of things here. I'm going to skimp on my own science and just try to give you a broad overview of exactly what we're going to try to provide for you guys. So the contents, the roadmap, in particular already we have surface met, the observations that our team took out on the ice sheet at various stations. So temperature, relative humidity, wind speed, the derived fluxes from the high frequency wind speeds, so turbulent and surface fluxes. Then we also have the SON profiles. So we've worked on creating a merged SON data product. So similar to the plots that Ula showed, where you have the time height cross section available to you, and an interpolated time height cross section from SONs is available inside of the product. And then moisture profiles is derived from ARM instrumentation for liquid water path and precipitable water vapor, as well as working on getting snowfall rate. So the future hopefully will look like getting even more detail into these processes. So cloud microphysics, continuous wind profiles, ice and ocean parameters, like I mentioned. But I want to specifically mention, of course, since we are at the ARM ASR meeting, just how much of the ARM work has gone into this product. So the radiation observations at Met City were done by ARM and DOE on the ice sheet via IceRad and SkyRad, the Quasar radar on the ship, the microwave radiometer on the ship, and the soundings were all joint ARM products, joint ARM ventures that are going into the data product. And then hopefully soon aerosols and more. So yeah, if you're interested in this type of thing, send me an email. I have a poster presentation that goes into a little more detail. I'm already using this data product for a few of my science goals. So the Plinia opening in 2020, I'm working on a synoptic climatology for the whole of MOSAiC. These types of things. If you'd like to talk about any of that, catch me in the poster session or by email. Thank you.
Great, thank you, Michael. Any questions for Michael about that data product? Okay. Wow, well, so we made it through a lot of fantastic little snippets of science there. Thanks everybody for providing those perspectives. I think that, you know, it's clear to see that there's lots of great science that can be enabled by the observations that were made at MOSAiC. You can see touching on almost all the themes that DOE, ARM, ASR are interested in. So it's great to see work progressing there. But also I think that you can see that there's much more to be done. And, you know, it's been really great to see the number of participants in this session. And I would hope that further people would be motivated to dive into these great data. And with that, we'd like to kind of open up the floor for more discussion, more questions. You've seen all these different presentations. So if you have specific questions to individual presenters or about the data or about other pathways forward, please feel free to bring those forward. And ideally, I mean, you can raise your hand or add something into the chat. I see there's been some nice chat dialogue going on so far. So does anybody have anything that they'd like to bring up or any questions they'd like to pose to any of the presenters?
Heis, go ahead. You have your hand raised.
Yeah, thanks, Jessie and Matt. I was thinking about how previous campaigns have kind of worked their way through the ARM system after data are collected and through the ASR science system. And one of the things that always seems to bubble up are these model intercomparison studies, case studies. I wonder whether there's been any discussion in that direction or whether maybe that's something that we should think about at a future meeting, either a separate offline meeting or something else. I wonder if you guys have thoughts on that.
I think that's a great question. And I would put it out to some of the modelers. I know there's a number of modelers on the call here. First off, do you see that there might be some data that would be interesting and useful to feed into your model studies? But to Heis's point, we've learned a lot from model intercomparisons in the past. Most importantly, I think it brings a number of modelers to the table under some shared concept, some shared science focus. And I think that at some level, we haven't necessarily developed what that is yet, but I would be interested to hear from any of the modelers on the call if you think you see something interesting here, some interesting areas to focus on. Jim, I see you just put a chat. Would you like to say that verbally?
Sure, Matt. Yeah, so as I think you know, and Heisen I'm sure knows, as we're looking at next cases for LASSO, MOSAiC was definitely one of high interest. We put it out there a few years because we wanted the data to mature, but it's certainly something I'm sure we would like to talk more about. So I think that would be something we should discuss in the same context.
Yes, I agree. Ula.
Yeah, I know a lot of field programs have had model intercomparisons, and I think they are useful. We learn a lot about the models, but I think often with a field program, a large field program like this, I think the initial part is really trying to see if specific models can actually reproduce what's in the observations. And so, for instance, in our project, we are doing that kind of side by side with for instance, identifying these events that have ice dynamics going with them. And then we're seeing Amy is pulling out the data from the pseudo operational model runs and seeing how well the CAFS model capture that. And also both the atmospheric part and the sea ice part, because it's a coupled model. And so I think, some models are not coupled. And so you can't expect them to be able to do the things that are where coupled processes are really important. But developing or showing the atmospheric structures, I think that is something that we can do at this point. We're starting to get the observations in shape now and starting to look at that. So rather than doing a broad model comparison, I think comparing to the observations is the first step.
Yeah, that's a great point. I see a couple other comments in the chat. I believe that's probably Steve Klein. Klein21 is talking about coupled modeling of fast processes again. So, and Joe Sedler talked about model evaluation focused on dynamics again, which is a highly coupled process. So I think that this whole notion of coupled processes, right? That's kind of how MOSAiC was designed, and I think it's a tremendous opportunity to look in high detail at coupling processes. And so you can imagine a variety of different approaches that one might take there. So perhaps that's a path forward. I see, Mark, you have your hand up.
Yeah, just a quick question, since it seems like there are at least 2 members of the quote unquote flux or surface flux group. I was wondering, could you just give a little bit more of information on the network of sensor flux that measuring turbulent fluxes that you had out there? And what was kind of the arrangement or spatial distribution of them? Thank you.
There were a couple of different approaches. There was the main installation on the ice near the ship, which was as continuous as possible, and that would be kind of the primary node. But there were other nodes that were distributed out, sometimes about 15 kilometers away in different directions from the ship, and those were largely operated in the wintertime. Ice dynamics did some damage to that network over the course of the year, and then some of those stations were redeployed closer in, at closer scales to look at kind of smaller scale heterogeneity in surface fluxes. And then there was another set of surface flux measurements made by some collaborators from Germany as well. So over the course of the year, it changed a little bit seasonally, but there were multiple perspectives capturing multiple scales of surface energy flux and surface energy transfer.
Thank you.
Amy.
Yeah, I just wanted to say that there are a number of different model intercomparison activities that have already been started through the year of polar prediction. So there's this wintertime statistics case that I talked about, as well as the next stage of this is looking at a moist air intrusion event that happened, I believe it was at the end of April. And I'm not really sure how to coordinate that with the DOE activities, but we would be very interested in discussing that with you.
Yeah, that's a great point, Amy. The warm air intrusion event is a focus for a number of people within the polar prediction project. And so that could be another area that's of great interest for model intercomparison, both because of a really interesting and impactful atmospheric process, a warm air intrusion into the Arctic, cloudiness and all the associated features there, but also because of the highly coupled interactions with the surface. And so you can imagine a kind of a coupled model process focus on this event because it does affect the whole coupled system. So yeah, that's a great idea. Are there other thoughts about kind of model focus areas? And truthfully, it takes a little time to ramp these up, and I think that's fine. We need to chew on the data a little bit, get them all in good shape, but we're really well along that path. But one could imagine perhaps next year at the time when we get to meet together all in the same room, face to face, we might actually be to a point where we have the data that's prime and ready to actually start to think about organizing kind of a more coordinated model intercomparison work. Any other thoughts on that topic?
May I ask a question?
Yeah, Sean.
Yeah, also it's more or less related to the model work. So we care about the snowstorm and their contribution to the particles and also to the CCN. I don't know if some of you are interested to get some model work to help us understand the process, how the snowstorm contribute to not only to the larger particles, but also to the smaller particles. I don't know any of you are interested in that. Yeah. We already finished our part. We found that snowstorm not only bring to the larger particles, but also contribute to the smaller particles. And the smaller particles can also be active to the CCN. Overall, that during the snowstorm, there are strong sources of the CCN during the polar night period. So we are really interested if the model work, or maybe some people who measure the chemical composition also can give us more information.
Okay, so she
concerning the
can't close it.
aerosol property. Yeah.
So then you're looking at things like wet deposition and interactions between snowfall and the aerosol population.
Yes, and also especially their contribution to CCN. Yeah, we found pretty high CCN concentration during the polar night when they have strong winds.
That's a great topic, one that's really fascinating. I know there's a number of people interested in the storms and characterizing precipitation And so potentially there would be some people that'd be interested in interacting with you and looking at the effect that has on the aerosol population. I don't know if anybody has any comments on that. Ula.
Yeah, I was curious. This is a really nice point about the aerosols. I know, for instance, I think the storm you're referring to is a mid-November cyclone. Is that correct?
It's not only in November, it also happens in December, January, and February.
Okay.
Mainly during the polar night period. Yeah, we have several phenomena. Yeah.
Okay. I've looked at a few of those at least, like the November one and also early February and in January. There's often a change in air mass associated with those kinds of events. And so I'm curious if you've done any trajectory analysis. I think could be really important to understand if this aerosol or the aerosol transition you're seeing is really primarily due to a change in the transport origin or not.
Yeah, it's a good idea. Yeah. From our data, we see that because usually the wind gets strong first, and then the high concentration of antigen accumulation will follow this trend. So they don't start at the same time. So we think about this might be a regional phenomenon, not from the local, but we haven't confirmed that. We need some model around to help us understand the whole process, how the snowstorm brings the small particles.
Yeah, I think that's right.
Yeah, thanks.
Yeah, great. And I see Hailong made a comment as well, where the HILAT project is also interested in water vapor intrusions and impacts on surface energy budgets. So yeah, that's great. It seems like there's a lot of interest in some of these coupled processes, warm moist intrusions. And so I think this really will point us in a direction. That's how we might want to organize some of the kind of larger group activities, or at least focus areas for the future as we go forward here. So yeah, thanks for all that input. We are winding towards the end of our session here. And wonder if anybody has any other final comments or thoughts or questions in our last 2 minutes. Well, I'll just say that it's been really fantastic to work with such a diverse group of people, both internationally and across the whole DOE ARM ASR community. It really makes science fun and exciting. And I hope that we see the community continue to grow. I know there's been some nice FOAs out there suggesting research in the polar regions and the Arctic. And I hope that people continue to write great proposals to do great science, because I think you can see there's a ton of data here, certainly way more than any of the people that are already working on it can digest. So we need more of you to turn towards this data set to unlock some of these mysteries of the Arctic. So thanks so much for your participation today and in the discussions that we're having all week here. I can't wait until hopefully next year when we can actually see each other face to face. I really look forward to that time as well. Thanks to our speakers and all the other contributions that have been made to this session. And we'll say good day to you all and see you in other sessions. Thank you.
Thanks a lot, Matt. Have a good one.